Okay, I want to go through the problems that I gave you on the review packet last time. So we'll start off with, we had graphs, determining the limit from a graph. Now, when you look at a graph and you notice things like this, you notice there's a jump there. If you're coming from the left, you're down here. If you're coming from the right, you're up here. That means the limit's not going to exist. Use this part of the graph to get the left-hand limit, this part to get the right-hand limit. But you notice they're not going to be the same. So, right away, the limit doesn't exist there. Now, let's think about the limit as x goes to -1. If you're going to -1 from the left, okay, so x is approaching -1 from this way. Well, what's the graph doing? Well, there's nothing down here. You look up here and you're right here on this curve. And where do you end up? You end up at 1. So that limit's 1. Now, if you go from the right, you're coming from the right, the graph, there's nothing above you, but below you is this. So you're on this graph and you end up at -1. Now, because those are not the same, 1 and -1, you say that this limit here does not exist. Now, as far as the function value, well, here you've got an open circle and here you've got a closed circle. So that's what the function value is. The function value is 1. Now, you look over here at 2. So if you're approaching 2 from the left, you're on this curve right here coming from the left, and you notice that that's going to be 1. Okay? If you're approaching from the right, you're up here, and you notice that's 3. Therefore, the limit overall does not exist. And f of 2, it looks like is 2. So that's what you need to keep in mind when you're looking at the graph trying to determine a limit. Now, let's suppose we've got an expression like this and we're trying to determine the limit. Well, what you think about is, I wonder if I can just plug in and get a value. In other words, I wonder if I can, in this case of a here, I wonder if I can take the limit of the top, which is just 3 plus 3, over the limit of the bottom. And you can, as long as you don't get as long as you don't get something like 0 over 0, or a 0 in the bottom. So you've got 6 over 10, and that would be the limit. All you do on that one is plug in. Now, when you come to this next one, b, you'll notice that if you put a 3 in the top, if you take a limit of the top, plugging in a 3, you're going to get 0. If you take the limit of the bottom, you're going to get 0. So that tells you that I need to factor and cancel. So we get x minus 3 times x plus 3 over x minus 3. See, normally, if you have a rational function like this one right here, if you can plug in and get a number, not 0 over 0, but if you just get a number like 610, you're good. If you've got a rational function like this one and you plug in and get 0 over 0, that tells you there's something that you need to do. You need to do some work before you can get at the limit. In this case, we factor and we notice we can divide out that x minus 3, and then we can plug in. And we get 3, plug in and 3 there, plus 3, and that's 6. Now, C is another example of that, where if we put in a -2 up top, we get 0, a -2 on the bottom, we get 0. So we got some work to do. So I'm going to factor the top, and I'll factor the bottom. It's a difference of squares. And then you notice those cancel. Now we can plug in the -2. -2 plus 3 over -2 minus 2, and you get 1 over -4. Okay? So we're just factoring and canceling. And what we're finding, what's going on here is, in this graph, there's a hole in the graph right at -2. So when we factor and cancel, what we're doing is we're removing that part that makes it 0 in the bottom. Now, let's look at this. So on those previous ones, we had just one polynomial over another. And if we can, in a case like this, plug in if you can, and if you just get a number, good. Otherwise, you have to factor and cancel. Now, let's look at this. These are not polynomials over polynomials. These are, you've got these compound fractions, or in this case over here, a radical. So there is a trick for each one of these to get at the limit. When you have this fraction within a fraction, like this first one right here, what you want to do is multiply by the common denominator, which is 2x. So here's what I'm going to do. I'm going to multiply everything by 2x. See? And what you're really doing is you're multiplying by 2x over 2x and just distributing the 2x through. Now, when you do that, notice some things cancel. There, the x cancels. Here, the 2 cancels. And what you're left with is the limit as x goes to 2 of 2 minus x over 2x, x minus 2. There. Now, we can almost plug in, but notice we still get 0 over 0. So and by the way, we would just try to plug in on this one, but we get 0 over 0. See, so you always try just plugging in first. Now notice this and this divide out, but not exactly, because 2 minus x and x minus 2 are opposites. So when we divide out, we have to replace it with -1. And what we get now is the limit as x goes to 2 of -1 over 2x. Plug in the 2 and you get -1/4. Okay. Now we do the same thing over here. I'm going to multiply by 2 times 2 plus x. And I do it all over for everything. Because it's like we're multiplying by 2 times 2 plus x to the top and bottom. And we distribute it to each term. So here's what we got now. Now, notice that this one and this one cancel, this one and this one. So let's see what we got now. We've got the limit as x goes to 0 of 2 minus, now watch out, put this whole thing in parentheses. Now, you have to really watch your bad self at this point, because some people might try this. No, you can't do that, right? Because this 2 plus x up top is being held to this 2 over here by minus, and you can't just break that bond with dividing. So what you have to do is you have to simplify the top. So here it goes. We've got the limit as x goes to 0 of -x over 2x, 2 plus x. See, because those 2's got rid of each other. Now the x's cancel. Well, that solves our problem, because now plugging in a 0 will not give us 0 on the bottom. What we get is -1 up top, and on the bottom, 2 times 2, or -1 over 4. Okay, so notice that's the way you deal with these types, where you've got like a compound fraction, a fraction within a fraction. Now we've got a radical over here. The way we deal with that is multiplying by the conjugate. Because the thing is, if we multiply the square root of a minus the square root of b, if we multiply that by the square root of a plus b, square root of b, what we get is the first term squared minus the second term squared. And notice the radicals are gone. This is like a difference of squares factorization. When you multiply something by its conjugate like this, you get the first term squared minus the second term squared. So we do that here. We've got the limit as x goes to 0 of 4 plus x minus 2, square root of 4 plus x plus 2, and we do that same thing to the bottom. 4 plus x plus 2. See, I do that to the top and the bottom. And what I get up top is I get the first term squared, which is 4 plus x, minus the second term squared, all over all this on the bottom. And we don't want to multiply this out. Just leave it as it is. Okay. Now, when we do that, notice that this 4 and this 4 divide out, or not divide out, but add out. And what we get is the limit as x goes to 0 of x over x square root of 4 plus x plus 2. These x's divide out. And now we can just plug in and we get 1 over 4. See? Just plugging in a 0 for the x. Okay, here's another one. Now, I'll go through this one a little more quickly. We multiply by the conjugate. And when we multiply by the conjugate, what we get up top is the first term squared minus the second term squared. And then the bottom, we just get x times the conjugate, like that. And once again, we get the limit as x goes to 0 of x over x, square root of 9 plus x. There. And this would be 1 over 6. Okay? Yeah. So those are some special cases. Now, h, here we've got a polynomial over a polynomial. And this is just the old, we did a couple of these earlier, but you just factor. Okay, factor the top, factor the bottom. Okay. And then you'll notice these cancel. So then you can just plug in and we get 3 over 1. So that limit is 3. Yeah, that's it. Okay, now remember we've also got some celebrity limits that we need to be familiar with. This is one of them. This is the limit as x goes to 0 sine x over x. That's 1. This one is another one. This is 0. So those two limits are those are a couple of limits you need to have in your mind. Now, built on this, we get limits like this one right here. And what we can do with this is there's some manipulation that we can do to get this to where we can use this limit right here. But here's what you need to remember. You've got, notice, sine 3x over 2x. That limit is just going to be 3/2. And in fact, the limit as x goes to 0 of, well, let me just make it more general. And we looked at this before. A sine bx over cx. That limit is ab over c. We could just multiply through. It's like we just ignore the sine and the x and just take the product ab over c. Now, it's the same thing for this limit. This is just going to be 3 over 2. It's the same idea. It's built on this idea that limit as x goes to 0 of sine x over x is equal to 1. Now, we focused on that a little more earlier in the semester, so I'm just refreshing your memory so you can go back and look at that. Now, this one here, the limit, the absolute value of x minus 2 over x minus 2. Well, if you think about what that looks like, right here is 2. If you choose any value of x bigger than 2, what you get is you get 1, because the top and the bottom are exactly the same value. Now, if you pick a value less than 2, what you get is -1, because the top is positive and the bottom is negative. Notice this jumpage, okay? that means that limit does not exist there. However, it exists anywhere else. So for example, at 3, this next one, you just plug in the absolute value of 3 minus 2 over 3 minus 2. Well, that's 1. So you just plug in on those. Now, we transition over here to the derivatives. These are both, of course, these are both limits, but if you think about it, this is the difference quotient. Remember, the difference quotient goes like this. It goes the limit as h goes to 0 of f of x plus h minus f of x over h. So this is the derivative of f at x. Now you could, you could put in some other value here. You could say f of a plus h. If you wanted to put in a particular value, and that's f prime of a. Well, this one is the same thing, except our function is cosine. This is saying the derivative of cosine at pi over 6. So this would be negative sine of pi over 6, which is negative 1/2. See, this is just requires us to say, hey, I know this one, this is the derivative. This one over here, this is the derivative of tangent at pi over 4. The derivative of tangent is secant squared. Yeah, so I believe that's going to be 2, because secant is the reciprocal of cosine. The value of cosine at pi over 4 is 1 over the square root of 2, or square root of 2 over 2. But then if you flip 1 over square root of 2, you get square root of 2, and square it, you get 2. Yeah, so there it goes. Now that brings us to the derivative. Okay, so we want to go through here and differentiate these functions. Now this first one, straight up power rule. Nothing more to it than that. B, straight up, this is derivative of sine, which is cosine. Nothing more to it than that. So you need to remember the derivatives of the trig functions. Now here is the product rule, this next one. So we've got x to the 4th sine x. So here we go. The derivative of the first times the second, plus the derivative of the second times the first. Okay? Derivative of the first times the second plus derivative of the second times the first. So there's the product rule thrown in there. Now down here we've got the derivative of tangent, which is secant squared x. The next one, not tangent x, but tangent 2x. That means the chain rule is involved. So you're going to have secant squared 2x times 2. Remember, the derivative of the outside, which is tangent, times the derivative of the inside. Next one, derivative of e to the x, that's just e to the x. E is not affected by derivatives. Okay, so derivative with respect to x of e to the x, just e to the x. Doesn't even care. Now, e to the x squared. Okay, so take the derivative of the e part times the derivative of what's up top. See, don't forget the chain rule. The derivative of e, just rewrite e. But then you have to multiply by the derivative of what's up top. Now, the next one, we've got a quotient. So we're going to use the quotient rule. The derivative of the top times the bottom minus the derivative of the bottom times the top, all over the bottom squared. Now, when you're talking about the bottom squared, you don't want to multiply that out. Don't multiply out the bottom. It'd be a rare situation where you would need to do that. So most of the part, you just leave the bottom alone. And now I just simplify everything up here. I've got negative x squared plus 1 all over x squared plus 1 squared. There we go. And I believe that's it. Yeah, okay. This one over here, we view this as x to the 1/2, and then we use the power rule. And we get 1/2 x to the negative 1/2. Okay, on this one, we've got the chain rule again because the derivative of cosine is negative sine. But then we've got to multiply by the derivative of the square root of x, which is 1/2 x to the negative 1/2. So, when you're trying to use the chain rule, you're thinking, well, if I were evaluating this function, what would I do first? Well, I'd find the square root of x. Then I'd take the cosine of that. So you're kind of going backwards. You're going to say, okay, derivative of cosine right here, derivative of this. And it's always multiplied. You're not adding these derivatives. They're all connected with multiplication. So this one over here, this is going to be secant 4x tan 4x. That's the derivative of secant. However, now multiply by the derivative of the inside, which is 4. So this is the chain rule. Okay, now this one over here, we've got cotangent squared. So we take the squared function first. So think you've got cotangent. If you were evaluating this function, first thing you would do is find cotangent. Then you would square the result. So you go backwards. You're going to take 2 cotangent x times the derivative of cotangent, which is negative cosecant squared. Yeah, okay. Okay, here we've got cosecant to the 4th, 2x plus 1. So we're thinking, okay, if I'm evaluating this function, I'm going to find 2x plus 1. Then I'm going to find the cosecant, and then I'm going to raise it to the 4th power. So we're going backwards from that. We take the 4th power. So 4 cosecant to the 3rd, 2x plus 1. Check, got the 4th power. Now the derivative of cosecant. Well, the derivative of cosecant is negative cosecant cotangent. Now notice I keep the 2x plus 1. That doesn't change. Times the derivative of the inside, okay, which is 2. And then you can go ahead and simplify this. You get 8, well, negative 8, let's say, negative 8 cosecant to the 4th, 2x plus 1 times cotangent 2x plus 1. Yeah, we can do that. Put them together. Okay, now this one, we've got the derivative of the outside, which is 4 2x plus 1 over 3x plus 4 to the 3rd. Okay, that's the derivative of the outside. Now the derivative of the inside. Quotient rule. Derivative of the top times the bottom minus the derivative of the bottom times the top, all over the bottom squared. Now you can simplify it a little bit. You've got 4 times 2x plus 1, whoops, over 3x plus 4. And then inside here you've got, I guess 5, right? 5 over 3x plus 4 squared. Yeah, 8 minus 3. Now we could, oh, by the way, there's a cube right there. So we could go a little further and say, okay, so this is going to be 20 2x plus 1 to the third over 3x plus 4 to the fifth, putting the third power and the second power together there. Okay, now over here we've got just 1 over x. That just requires us knowing what the natural log derivative is. Okay. Now here we've got natural log of x to the fourth. I recommend this. Rewrite this as 4 log x. In other words, use that property of logs, because now notice what we can do. We can say, okay, the derivative is just going to be 4 times 1 over x. Now, the alternative is we could say 1 over x to the fourth times the derivative of x to the fourth, which is 4x cubed. And notice it still reduces to the same thing. You get 4 over x. So same thing. Now, I would use the properties here as well, because notice what you can do now. You've got log 3x plus 1 minus log 4x plus 5. Here, using the properties is very helpful because it just makes for neater work, easier. Okay, so otherwise you have to put 1 over this whole thing times the derivative of that whole thing. But now notice this is going to be 1 over 3x plus 1. That's the derivative times 3 minus 1 over 4x plus 5 times 4. See, it makes things a little bit easier. So there's the derivative. So if you use these properties of logs, that makes things a little bit easier. Remember, so we've got log of uv is equal to log u plus log v. We've got log u over v is equal to log u minus log v. And then, of course, we've got log u to the r. These are important properties. So over here, you've got 7 log 4x plus 5. Now we take the derivative. 7 times 1 over 4x plus 5 times 4. Okay, here's another one. Okay, so the log. So let's unravel this. So we've got y equals 7 log 4x plus 1 over 5x minus 1. Okay, now that's when I just brought the 7. Now let's unravel it a little further. This is 7 times log 4x plus 1 minus log 5x minus 1, which gives me 7 times 4 over 4x plus 1 minus 5 over 5x minus 1. Okay, so there we've used some properties of logs with those. Now, I'm going through this kind of fast because I know that you can't always, watch it again. You can slow down the video, but I'm trying to get through as much of this as I can. Now, on this one, this is not a power function, where we have x to some power, like x to the third power. And it also doesn't fit the exponential uh, formula, right? This is not like 2 to the x. This is x to the x. So what we do here is I take the log on both sides, because what I want to do is I want to bring the x off of that exponent position like that. Then I implicitly differentiate. So here, log y, 1 over y prime equals the derivative of x, which is 1. I'm using the product rule, plus x times the derivative of log x. So here we've got this. We've got 1 over y prime equals log x plus 1. Now, what I can do is multiply by y. I've got the derivative. And when you consider that y is x to the x, here's what your derivative looks like. There it is. Now we do the same thing over here. We've got log y equals sine x log x. Once again, we differentiate 1 over y prime equals cosine x log x plus sine x 1 over x. Multiply through by y, and we get y prime is equal to x to the sine x cosine x log x plus sine x over x. And there we have it. Okay, okay. Some more logs. This one is log 3x plus 1 to the 1/2. Now, if I use my properties of logs, bring that 1/2 out front, that derivative just becomes a little puppy dog, right? It's easy. So now we have this. We have 1/2 3 over 3x plus 1. See? That's the derivative. This one over here has got a lot going on with it. Here's what we've got. We've got y equals log x squared plus log x plus 1 to the 1/3. Okay, so I broke it up using the addition property. Then I've got y equals 2 log x plus 1/3 log x plus 1. Now, this is a lot more manageable. So if we're talking about the derivative, it's going to be 2 over x plus 1/3 1 over x plus 1. There we have it. Now, we've got quotient rule here. I've got the derivative of the top times the bottom minus the derivative of the bottom times the top, all over the bottom squared. Okay, so I just went through there differentiating. Now, what I like to do is when I'm simplifying this, I like to multiply. Notice I've got a 2 in the bottom here, so I'm going to multiply everything by 2. And I've also got this x to the 1/2 in the bottom, or negative x to the negative 1/2. So I'm just going to multiply by x to the 1/2. And when I do that, notice what happens here. I get 2x minus, now this cancels with that. This and this make x to the 0. So I just get x plus 1 here. And then down in the bottom, I get 2x to the 3/2. And there's my derivative right there. So it's just a little trick of simplifying. Okay. Now, for this one, we've got, of course, y equals 2x plus 1 over 3x plus 1 to the 1/2. So here I go. The derivative is going to be 1/2 2x plus 1 over 3x plus 1, whoops, to the negative 1/2. They just using power rule, times the derivative of the top times the bottom minus the derivative of the bottom times the top, all over the bottom squared. And then you can simplify that. For the sake of time, I'll just leave it like that. Now for this one, we've got the chain rule. So let's see what we would do first. If I were evaluating this, I would go x squared plus 1, find that. Then I would raise that to the fifth power, take the sine of that, and then raise that to the fourth power. So I'm going to go backwards. So here I go. I've got 4 sine cubed x squared plus 1 to the fifth. Derivative of sine is cosine. Check. Then I've got this thing, 5x squared plus 1 to the fourth, and then times 2x. So you're just working your way from the outside in. Okay, so that's some, just kind of an overview, a bunch of different derivative problems, basic derivative problems. And you can let me know if there's a particular type you want to practice more on. Now, we also talked about graphing and finding uh, maxes and mins and that sort of thing, critical numbers. Remember, critical numbers are found by taking the first derivative and setting it equal to 0. In this case, we've got x squared plus 7x plus 10. And I set that equal to 0, factor it, and I get my critical numbers, -2, -5. Those are my critical numbers. Now, what I do with that, I use that to divide the number line. So I've got -5, -2, and I just pick test numbers. So this divides the number line. Everything less than -5, maybe not -6. Everything between -5 and -2, maybe -3 is a good test number. And everything bigger than -2, maybe 0. And what I do is I plug that back into the derivative to see if I get positives or negative. Positives mean the graph is increasing. Negatives mean it's decreasing. So here I go. I'm going to test these numbers, -6, -3, and 0. And I'm going to plug them into, I like to plug into the factored form. Now, if I plug in a -6, I get a negative times a negative, which is a positive. That means the graph is increasing there. So so far I've got this negative infinity to -5. That's where the graph is increasing. Now let me put in the -3. I get a negative times a positive, which is a negative. So intervals over which the graph is decreasing so far, and I think this is going to be it. There's where it's decreasing. Now, if I put in a 0, I get a positive times a positive, which is a positive. So I add this on, 2 or -2 to infinity. There we go. Now, use the first derivative test to determine where we have a maximum. Well, we have a maximum whenever the graph was increasing and then it starts decreasing. So it hit a max at x equals -5. Okay, so x equals -5. Where does it have a min? Well, wherever it was decreasing and all of a sudden it starts increasing. X is -2. Now we want to talk about concavity. So we go back and get x squared plus 7x plus 10. So here we go. So f prime of x equals x squared plus 7x plus 10. Now we're talking about concavity, so we talk about the second derivative, which is 2x plus 7. We set that equal to 0 to get not the critical numbers, but possible inflection numbers, places of inflection. So we get x equals -7/2. Okay. Now, where is it concave up? Well, the number line is divided. Everything less than -7/2, everything bigger. I'll pick -4 over here. And I'll pick 0 over here. I just need a number less than, -3.5. -4 fits the bill. and then everything, any number bigger than -7/2. And then I analyze those numbers. So I've got this. I've got, let's see here, I've got -4 and 0, and I want to plug those into 2x plus 7. Now, if I plug in a -4, I get a negative, right? If I plug in a 0, I get a positive. So where is it concave? Where is it concave up? Well, from -7/2 to infinity. See, right here. Where is it concave down? From -infinity to -7/2. Now find the value where you have inflection. Well, x equals, whoops, let's see here. Okay, x equals -7/2. That's where everything changes. Now the second derivative test just simply means, look, we take the critical numbers that we got up here, -2 and -5. So I plug in a -2 and I plug them in here into the second derivative. Now that gives me a number bigger than 0. That corresponds to a min, okay? Now over here, I plug in the -5. That gives me a number less than 0, which corresponds to a max. So min, max, okay? Now, we also had on this packet a related rates problem, a sphere which has a volume of 4/3 pi r cubed is increasing at a rate of 4 cubic centimeters per second. So what they gave us in calculus speak is dV dt is equal to 4 cubic centimeters per second. And that's when r is equal to 2. So when the radius is equal to 2. And what they want us to do is they want us to find, okay, well, how fast is the radius changing here? Well, we differentiate. So we've got v prime is equal to 4 pi r squared r prime. Okay? So we look upon r and volume as both functions of t. So every time we differentiate an r, we're going to tack on an r prime. Whenever we differentiate something with v in it, we tack on a v prime. Now I just put in everything. So let me just leave off the units here. We've got 3 cubic units. I mean, no, 4. 4, I'm sorry. We've got 4 cubic units per second equals 4 pi. R is 2 r prime, and what we're trying to do is solve and find r prime. Notice that these 4's divide out, and what you get is you get 1 over 4 pi centimeters per second equals dr dt.